Hey, good morning, sunshines, and good afternoon, fifth hour sunshines. I'm going to go through numbers 2, 3, and 4. Hopefully you took some time, gave an honest attempt at those. I'm going to really be focusing on why I'm making the decisions I do, and why, rather than just simply whether we got the right answer. I'll also be going back to the notes that were made in yesterday's video, especially the part that has this curve. It's weird that they call this a curve. It looks like it's some straight lines. I don't know why they call it a curve, but this is called a heating curve. How do they know it's a heating curve? Because as time goes on, the temperature goes up. What about a cooling curve? What would that look like? I'll just draw a really short one or a smaller one over here, but it would still have the numbers 100. It would still have the numbers 0. All right, I hate doing this. But if we were really cooling curve, it would start at some hot temperature, cool off to 100, and fuse together. No, it wouldn't fuse, it would condense. Cool down to 0, freeze, and then get even colder. This is a cooling curve. This is a heating curve, just based on the idea that the temp is going from low to high versus high to low in the cooling. Okay, your mission was to attack a problem like this: a 92-gram hunk of ice at 0 Celsius allowed to melt and come to room temp. How much heat did it absorb? Well, one thing that we're going to see really quick is this is nowhere near as in-depth as a 5-step problem. So what this drawing the heating and cooling curve, like the direction said to do, helps us do is to figure out how many steps it is. It's not so that the teacher knows what you know. It's so that you know what to do. A 92-gram hunk of ice, that doesn't belong on the chart. The chart's going to be time and temp, or degrees Celsius, which is temp. You don't have to label it. I'm doing it so we understand. It's at 0 degrees Celsius. I'll just put a 0 here. It doesn't matter where it's at. And it's going to melt, and then it's going to come up to 22 degrees Celsius. So I don't need 100 or 110 or negative anything. Those are the only numbers I need. So we got a hunk of ice, and it's at 0. And so you add some heat, and it doesn't do anything. It just melts, and that's what we saw. A plateau is a phase change until it all melts, and then it heats up, and they're just saying we're going to stop at 22. And it's going to ask you, how much energy? Well, let me tell you, that is 2 segments. So that's going to be a 2-part problem. We will figure out how much energy it takes to do number 1, figure out how much energy it takes to do number 2, and just add those 2 numbers together. Each time, we're dealing with 92 grams. 92 grams, 92 grams. They're both going to be dealing with the same 92 grams. What's happening at 1? Okay, 0 degrees Celsius. If I went back to my notes, maybe you want to add this to your notes. Melting and freezing are part of a process called heat of fusion. If you add heat, it'll melt. If you take it away. But the heat that needs to be added or subtracted is called fusing. Up at 100 degrees, we could say that it evaporates. We could say it condenses if we cools it off. We could even say it vaporizes. But it's called heat of vaporization. And so we have to figure out which of these numbers we're going to be using. So 92 grams. So at number 1, it's at 0 degrees Celsius. The 0 degrees portion is called fusion. Now really it's melting, but the amount of heat that needs to be added is called the heat of fusion. For the substance called water, H2O, which is ice, that number is 334 joules per every gram. It takes 334 joules to melt 1 gram of ice. How much would it take to do 92? Well, we just multiply them. Next up is number 2. We have a phase change. No, I'm sorry. We have a temperature change. Anytime we see a slope part instead of a flat plateau, which would be a slope of 0, if there's a slope, it's going to be a temperature change. So I have to utilize the m times c times delta t. I already wrote the mass, 92 grams. What is the specific heat? Well, it depends. Are we dealing with a solid or liquid or a gas? Well, you have to answer that question for yourself. If you had some ice and you melted it and it was up to a 22 degrees Celsius, what phase? That's going to be liquid, 4.18 joules per grams times degrees Celsius. So I have to use 4.18 because at those temperatures, water, H2O, is a liquid, 4.18. How much is it going to change? It's only going to change from 0 to 22, which is a change of 22 degrees Celsius. Next step up, I'm going to pull up this little calculator. 92 times 334. That number is 30,728. That would be joules because grams and grams is going to cross off. The other one, 92 times 4.18 times 22, 84, whoa, that just seems like a strange number, but okay, 8460.3, I'm just going to round, 8460.3 joules, because grams and grams, and degrees Celsius cross off, joules is the only thing left. 8460.3 plus 30728, 39,188. 39,188.3 joules. I hope that's right. First time I've done that one, at least this year. Okay, on to number 3. How much energy would it have to be removed? And so we're not going to deal with negative numbers. We're not talking about negative energy. We're just going to take away energy. How much? Okay. I don't know what to do with numbers until I draw my heating or cooling curve. I'm removing heat, so it's going to be cooling. But more importantly, it tells me that it's going to start at 135 Celsius, make a 135, and it's going to turn into ice. Holy Cthulhu, this is going to be a tricky one. Negative 135 degrees Celsius. This does not have to be to scale, but 0 would probably be, I don't know, up here somewhere, and 100 would probably be up here. It does not necessarily need to be to scale, but once I put it there now, I'm going to try to document what happened. I had steam. First, you take heat away and it will cool off. When it gets to 100, it will condense. When it all condenses, it will cool off to 0. When it gets to 0, it will freeze. And then once it freezes, it will cool off, and not to negative 35, but to negative 135. This is a 1, 2, 3, 4, 5-step problem. These are going to be some big numbers because unfortunately somebody thought we should have a huge chunk of ice. It's 500 grams. That's just over a pound. So 500 grams. Now since it's a 5-step process, I know that because I drew the cooling curve and based on the numbers that they told me, and there's going to be 1, 2, 3, 4, 5 segments. I'm going to write 500 grams, 500 grams, 5 times. Just get it all set up. The process. You learn a process in any sort of job that you do, and then get good at going through the process to get the job done efficiently. Okay, next thing is this. Some of these are plateaus, flat spots, phase change, numbers 2 and 4, for instance. The others, 1, 3, and 5, there's a slope with the line. There's a change in temperature. All the ones, like the first one, the third one, and the 5th one, are an M times C times delta T. It's not required that you write these MC delta T's. I'm doing it to try to guide myself. If you know you struggle with math, you should probably do it. Maybe it will help guide you along the way and help you get some of the numbers in the right place. But some of you will find it's not necessary to write MC delta T. How about the other parts? Well, in number 2, that's when it's condensing. But this heat that we took notes on was called something called heat of vaporization. And so I generally like to write the word and get used to using the word vaporization. So I'm going to write vaporization here. At number 4, it's at 0 degrees. So that's the freezing part or the fusion part. If they fuse together, that's the same as freezing. Okay, lots more work left, but I have a plan. The first one is m times c times delta t. A couple of questions I ask myself. At the first step, what phase is it in? Well, it's over 100, it's water, and it's over 100 degrees, and so it must be a gas. The gas is 2.1 joules per gram degree Celsius. That is the specific heat of a gas. I'm finding that on my notes. Ice, liquid, gas, or solid, liquid, gas are these numbers. You don't have to memorize those numbers. You get to use that piece of paper to find them. I just happen to know them, but I better keep referring to where I'm getting those numbers. So the very first section, 500 grams of steam, so that's 2.1 joules per gram degree Celsius, is changed from 135 to 100. What's the difference between 135 and 100? 35 degrees Celsius. I could do the math right now. I don't usually do it that way, but you're welcome to. You could put it into the calculator and write an answer and move on. I like to get everything set up and then just start what I call crunching numbers in the calculator. Next section is a plateau. There is no change in temp. The change in temp would be 0. And so that would make the answer 0. So what we need is the heat of vaporization. Go back to our notes. What is the heat of vaporization of liquid water? That is 2,200. I can't find it. Heat of fusion, heat of vaporization. Where did we write it? Did we not write it? That could really goof things up. Heat of fusion of water. Heat of vapor. Oh, there it is. There it is. 2260 joules per gram. Sorry about that. Just wanted to make sure I had my stuff in order. 500 times 2260 joules per gram. That one's set up. Number 3 is another phase change. No, it's not. I'm sorry. Number 3 is another temp change. So it's an m times c times delta t. What phase is the water going to be in between 0 and 100? That's a liquid. 4.18 joules per gram degree Celsius from the notes. How much will it change to get from 100 down to 0? 100 degrees Celsius. Heat of fusion for number 4. How much energy do you have to take away to freeze or fuse together? 334 joules per gram, except we have 500. These are going to be big numbers. Finally, the last one is an MC delta T. We're already dealing with ice, which is 2.1 joules per grams times degrees Celsius. And it's going to change not by 35 degrees, not by negative 35. It's going to change by 135 degrees Celsius. That's going to probably have tricked some people. So I should have an equal sign, an equal sign, an equal sign, an equal sign. I'm going to press pause and try to see if I can just get these crunched in there quicker and check back in. Not very smooth, I'd have to say. I won't guarantee that number. I think that's right. Showing my work would let me see, like if I do make a simple little mistake, I can see that I've got it mostly. That would be worth a lot of points on a test, and so a little calculator error here and there wouldn't be that big a deal. Last one. A 37-gram chunk of ice is heated from -8 until it evaporates. How much heat would it take to accomplish this? Step 1, start making a heating or cooling? Well, it's going to be heated up, so it's a heating curve. How cold does it need to be? -8. How hot is it ever going to get? Well, evaporates. What's that temperature? 100 is the hottest it needs to get. There's going to be something happening right there. So you're going to warm it up, and then it's going to melt. When it finally melts, it's going to warm up to 100, and then it's going to evaporate. And that's it. This is a tricky one too. This is a 1, 2, 3, 4 step problem. That means that I can take my 37 grams and write it 4 times. 1 has a slope, so it's an mc delta t. 3 has a slope, so it's an mc delta t. 2 is melting, or heat of fusion. 4 is evaporating because it's at 100 degrees, or heat of vaporization. Systematically going through here, we have 37 grams of ice, 2.1 joules per gram degree Celsius. Change in temp is going to be negative, it's going to change from -8 to 0. The change is simply going to be 8 degrees Celsius. That's going to be in joules. During the phase change, the melting one, it only takes 334 joules for every gram. Number 3 is another mc delta t, only this time, since it's at the temp between 0 and 100, it's a liquid. Some people might, actually the test will say to label the phases. So if you label those, it might help you. Liquid water is 4.18 joules per gram degree Celsius. How much is it going to change before something happens? 100 degrees Celsius, because it's going to go from 0 up to 100. Finally, at the end, it's going to vaporize. That takes a lot of energy, 2,260 joules for every gram. I'm just going to make an executive decision and say, if you've got all those numbers, you could do the numbers and add up those 1, 2, 3, 4 to get one number. I truly don't have the number for you. But check around, see what everybody has. I'm going to give you a practice test. It doesn't mean that there's a test very soon. It's the easiest way to give you something that would be workable on, and you can work on the practice test. It has some of these for the rest of the hour.